Okay, welcome back. So today we're going to talk about alkyne reduction a little bit more, specifically focusing on the mechanism of the dissolving metal reduction. So this was a case of lithium and ammonia, although sodium and ammonia, same mechanism, same results. And then we're going to talk about the hydration of alkynes. So first of all, alkyne reduction. So we talked a little bit about alkyne reduction, how you have H2 and palladium and carbon. It doesn't stop at the alkene, it goes all the way down to the alkane. And it adds the two hydrogen cis to each other. So technically you get this, but these molecules are the same molecule. They're just different conformations. If you treat this Lindlar's, you get a cis alkene, and it stops there. If you use the dissolving metal reaction, that's lithium, or it's actually also ammonia, lithium or sodium. Either one of those metals will do this, but the solvent that's used is ammonia. That gives you the trans, and stops there. So I want to talk first a little bit about this reaction right here with regards to synthesis. When you're working backwards, it looks like that's a reaction that you can always apply. So, for example, see a molecule like this. You can basically take any of these alkane fragments and make them into an alkyne. It looks awfully tempting when you're going backwards to do that. Please resist that temptation, because chances are the reaction's not going to work or lead into problems later on. For example, hydrogen and palladium and carbon does other things than what we've said. But first of all, I just want to say first, it does other things that we've said it does. For example, it not only reduces alkynes, it also reduces sp3X. So halides, or X equals chlorine, bromine, and iodide. I'm not mentioning fluoride because that's in a whole different ballpark. We won't be dealing with fluoride that much. But these other halogens will reduce those also to the alkane. So hydrogen, palladium, and carbon doesn't give you this product. Not only does it reduce the alkyne all the way down to the alkane, it also replaces the carbon-halogen bond with a carbon-hydrogen bond. So you have to be very careful when you're doing synthesis problems like this. Focus on the functional group that's given. Here you have one functional group that's a bromide. Use that. Focus on that. Otherwise, you end up creating a molecule with two functional groups, and that's infinitely harder to figure out because you have to worry about one and affecting the other. So Hydrogenation affects carbon-carbon pi bonds, except benzene. It affects sp3 carbon chlorine, sp3 carbon bromine, and sp3 carbon iodide bonds. And we replace those with hydrogens. Does not typically affect ethers, carbonyls, and alcohols. Now, I say typically. There are certain ethers or carbonyls or alcohols that are affected by that hydrogenation, but we will get into those when it comes time for Chem 345. For Chem 343, think of these groups as immune. Also, what's also immune to hydrogen and palladium? Benzene rings. Okay. So that's a warning. H2 Lindlars is poison palladium. It only affects alkynes. The dissolving metal reactions affects alkynes and also sp3 carbons attached to good leaving groups. To understand this, we'll need to discuss the mechanism of this reaction. Another thing that we also will need to talk about the mechanism of has to do with terminal alkynes. If you want to take a terminal alkyne and make it into a terminal alkene, you must use H2 Lindlars. If you use the dissolving metal reactions, you get a poor yield. Typically less than 33% yield. And so that also is explained by the mechanism of that. So, without further ado, the mechanism of the dissolving metal reaction. And the mechanism's the same regardless if you use sodium and ammonia. And so I'm going to use the mechanism saying to use sodium or lithium. So I'm going to use sodium in hopes of showing you that based off of another reaction that you already know. So we're going to go over the mechanism of the dissolving metal reaction. Now, it's called the dissolving metal reaction because that's what you do. You take ammonia, a solution of ammonia, and you add solid metal to it, in this case sodium. Solid metal, sodium 0, has a single electron. And what happens when you dissolve it in ammonia is the solution turns blue. The sodium's electron is popping off. It basically floats away in the solvent. And the reason ammonia is used is it turns out it's a very good solvent to solvate, or basically solubilize, electrons. It's a good way of getting the electrons to leave group 1 elements is by dissolving it in ammonia. And this electron is floating around. What happens with this electron is it bumps into the alkyne and it adds to the alkyne's anti-bonding orbital. So one way of thinking about it is this electron goes to one of those two carbons, it doesn't matter what. One of the pi bonds for the alkyne goes to that same carbon, and the other electron goes onto this, onto the other carbon. And what you end up getting is a carbanion on one end and a radical on the other end. This is called a radical carbanion. Now, carbon on the left is sp2 hybridized. It's connected, it has 3 electron domains, a carbon, and a lone pair. When we talked about radical stability last time, we talked about how radical stability mirrors that of a carbocation. Essentially, a single electron has a tendency not to cause rehybridization. You can think of this as sp hybridized. There's not enough electron density in that p orbital to force the other groups away from it, like it is here. So as a result, this geometry ends up being linear through that process. Now this carbanion is very basic, and so it deprotonates the solvent, ammonia, and you just get a radical. And then this radical waits around for another electron that's floating in the ammonia to come and combine with it. And it does so. The molecule flexes so that the two R groups end up away from each other, and you get a carbanion. And that carbanion then deprotonates ammonia and you get your reduced alkene. your reduced alkyne to give you the alkene. And it's a transalkene. And NH2 minus. So, if we were to balance this equation out based off of this mechanism, we have one alkyne plus 2 molecules of ammonia, because we used it twice. We also used 2 electrons, so therefore we needed 2 sodiums. And what we got out of it is this, plus 2 Na pluses, plus 2 NH2 minuses. Well, these are just an ionic compound, NaNH2. Where have we seen NaNH2? Think about that for a moment. Where have we seen this? What have we used it for? And the answer is we have used it in synthesis reactions to deprotonate terminal alkynes. And then we use the resulting carbanion in an SN2. This is the issue. This reaction right here, this deprotonation, is very fast. So, just say we were able to take 3 alkynes plus 6 molecules of sodium plus 6 molecules of ammonia. And let's do this cycle once. When we do this cycle once, and let's make it a terminal alkyne to show what we're doing. When we do this cycle once, we end up with the alkene plus 2 NaNH2s and then we have 2 remaining alkynes, 4 remaining sodiums, and 4 remaining ammonias. Well, the thing is, once you make this NaNH2 minus and this, these react right away in that acid-base reaction. And you get these carbanions. The first step in the reduction of the alkynes, or actually the reducing of the alkynes itself, is an electron adding to the alkyne. Electrons are negatively charged. This is negatively charged. This is not likely to add to that. They're just going to repulse each other. As a result, you're stuck with these that aren't capable of being reduced. And so as a result, you can at most reduce 1/3 of the alkynes. To terminal alkenes. The remaining 2/3 of the alkynes end up as carbanions and aren't reduced anymore, and so don't end up being converted. So this also kind of explains why you don't want to use lithium and ammonia with this molecule. Or sodium and ammonia for that matter. Lithium and ammonia. Well, first of all, ammonia can do an SN2 reaction with that. An H2 minus can do an SN2 reaction. It can also do an E2 reaction with this. And so as a result, you end up getting a mess and not that as a trans double bond. So just be very, very careful when using this. Also, this is a very, very common mistake. No, don't do this. This implies they are part of the same compound. It's not. Ammonia is the solvent, lithium is the metal. You can put it like this. You can put it like this. Or you can put it with a slash, or you can put it with a comma. But you need to distinguish that they are very different compounds. Okay. So, the next topic I want to talk about is the hydration of alkynes. So, we have covered some ways of doing alkene reactions, such as hydroboration. Or oxymercuration, demercuration. There are versions where essentially we're adding H and an OH across an alkene. Well, you can do the same thing across an alkyne. And you can do it anti-Markovnikov, where the OH goes on the less substituted side. Or you can do it Markovnikov, where the OH goes on the more substituted side. Except there's a slight complication. These molecules are what are known as enols. If we remember for the first chapter, first unit, enols are not alcohols. Enols are actually unstable compounds. They rapidly become something else. So I'm going to put brackets on these. What they become is they become carbonyls. The carbonyl form is a more stable form than the enol form is. And this mechanism right here, going from an enol to a carbonyl, is called tautomerization. And it's a little strange talking about tautomerization right now, because in a couple of days, I'm going to be talking about tautomerization for my Chem 345 class. And so tautomerization, you'll find, is going to be a significant part of Chem 345, and it's also going to be a part of Chem 343. It's going to be the same mechanism in both classes, so definitely be aware of this mechanism. So, how it works. Let's do the anti-Markovnikov one first. The anti-Markovnikov is the same conditions for an alkyne as it is for an alkene. The mechanism is very similar to the mechanism for an alkene. So you start off exactly as you would. Pi bond goes to the boron. The electrons from the BH bond go to the more substituted side. And as a result, you get a cis addition of hydrogen and a boron. And you have two more BH bonds. So you repeat this process. And place those H's with R groups. In this case, the R group is just this blue piece. Repeat it again and again. Now it's time for the oxidation of this. So you have the acid-base reaction between hydrogen peroxide and hydroxide. And this adds to the boron. Now here's the strange step. It's this rearrangement step where the carbon-boron bond, this bond slides over to the oxygen, and that kicks off the OH. Now the blue group was transferred over to the oxygen with the same stereochemistry. And then this process is repeated. Essentially what we've done is we've inserted an oxygen between the boron and the carbon. And now it's time for the hydroxide to come back in and adds to the boron. And one of these OR groups then leaves, because this is a Lewis acid-base reaction. That oxygen is falling on and off the boron, because that boron isn't happy having a negative formal charge. It's not happy having only six electrons. It's never really happy. So that's boron. And then you get this O-. So up to this point, the mechanism has been identical to the mechanism of the hydration of alkenes. Now, what would happen in the hydration of alkenes is you protonate that molecule, the O-. And that's what you do here, except this just happens to be resonance stabilized. And your acid, in this case water, can protonate either the O- or the C-. Protonates the O-, you get that. If protonates the C-, you get that as the product. Now, notice reversible arrows. We can use our knowledge of pKs to figure out which one of these is more favorable. So say the backwards reaction. OH- takes this proton off. It's an O-. Of course, it's resonance stabilized. And when that took that proton off, you get water. And then that C- takes that proton off. And get OH-. This molecule has a pKa roughly around 10. This is an OH attached to an sp2 carbon. The pKa of water is 15. So, equilibrium-wise, the reaction favors the right. Now, going backwards from this reaction, this hydrogen right here has a pKa around 20. This has a pKa of 15. So it's more favored to go this way than to this way. Notice this side is the more favored side. Makes the carbonyl the more favored constitutional isomer. By the way, this mechanism right here is called base catalyzed tautomerization. It's completely reversible. The carbonyl is in equilibrium with the enol, but the equilibrium favors the carbonyl side over the enol side. And you'll see this mechanism a lot in Chem 345. So, best to learn it now. Okay. Now, Markovnikov did. Oh, wait, before I continue on, say you have an alkyne like this and treat it with hydroboration. Both carbons are equally substituted. So expect a mixture of both molecules. But you get the difference when it's a terminal alkyne. Then you don't get a mixture. Because there's a definite difference in the substitution of these two carbons. Versus these two, there's no real difference in the substitution. Okay. Now I did the anti-Markovnikov addition of alkynes first, because those are the same conditions used for alkenes. When it comes to the Markovnikov hydration of alkynes, it's a little different. So with an alkene, the conditions are oxymercuration. It's a two-step procedure. The first step involves adding mercury acetate and water. Second step, let me actually draw this out. And then the second step is demercurization. I want to point out this blue carbon right here is sp3. And the carbon attached to the OH is also sp3. turns out that makes a difference. Enough so, the reaction conditions are altered. They're not the same. You still add mercury, and in this case it's typically mercury sulfate that's added. But the thing is, you don't need much of it. You just need a catalytic amount of mercury sulfate. Not much. As opposed to the reaction of alkenes, you do need a full equivalent. For every molecule of alkene you have, you must have 1 molecule of mercury. In the case of alkynes, you don't need that much mercury. What you do need is some acid and some water. And it's a single step. It's a single synthetic step. And that gives the ketone. So, how this mechanism works. First thing, think of mercury sulfate as a salt. Think of it as mercury 2+. Don't worry about the sulfate. Just think of it as mercury 2+. And this will react as a Lewis acid. A Lewis acid you can think of as a gigantic fluffy proton. Big H+. So, the mechanism is quite different from the mechanism of the alkene. What happens is the mercury binds itself to the alkyne. The pi bond leaps out and grabs the mercury. I'm not going to worry about the reversibility of arrows in this reaction. And the mercury ends up going on the end because it forms the carbocation on the more substituted side. And this carbocation is sp hybridized. If you form this intermediate, I'd accept it, but that is really, really strained, so unlikely. But once you have that, water adds. Chances are water is going to add from away from that mercury side and adds to the carbocation. It's adding away from the mercury side because, well, mercury is bigger than hydrogen. Then water takes the proton off. Again, we're not going to worry about the reversibility of these reactions. Okay. Now is where typically your strong acid comes in. And you're going to protonate the alkene, or technically, you're going to protonate the enol that you have here. So, what you can do, you can protonate, and it protonates to give the most stable carbocation it can. And the most stable carbocation is when the carbocation is right next to the OH, because that carbocation is resonance stabilized with this as the major resonance structure. Now, you can draw these molecules, since the resonance structures represent the same molecule. So therefore, you can go directly from this intermediate right to this major resonance structure. The way you do that is you add another arrow. Electrons from the OH comes down, swings these electrons over to the H, and that gets that. That's the same as adding this arrow right here, and that gets you right to this product right here. Now here is the difference between the two reactions. Between an alkene, another difference between an alkene and alkyne reaction hydration. This carbon right here is sp2. It's connected to a carbonyl. Well, it's a part of a carbonyl. It's connected to a double bond O. As opposed to here, it's sp3. What happens next is something that's not intuitive, obvious to a lot of students at this stage. That Lewis acid can come on and it can come off. In this case, it comes off. Now, it doesn't leave, it comes off. There's a very subtle difference. Leaves means it takes the electrons with it. They got leaving group leaving. And when you draw a leaving group leaving arrow, the electrons go with the group that's leaving. Well, the group that's leaving is actually the group highlighted in blue. The group that's leaving is leaving from the mercury. You can think of it as the mercury just falling off. Then what you have is the enol. Any way to generate the Hg2+, it finds another alkyne and the process repeats itself. That's why you only need a catalytic amount of the mercury salt. This is the enol. So we do what's called the acid catalyzed tautomerization process. We've sort of done it before. The electrons from the oxygen swing down, kicks these electrons over to the H, and over to there. And then, all that's left is to deprotonate. And that's the acid catalyzed tautomerization. I'm over time, but I do want to cover this one thing real fast. Tautomerization can be done in acid or base. Base deprotonates. Gives you an O-. O- swings its electrons down and it takes an H off there. Acid. The electrons swing down from the OH. These electrons, that kicks these electrons over to grab an H from an acid. Followed by deprotonation. Okay, these mechanisms look complicated, but all they are two proton transfers with a little resonance mixed in. Deprotonate to form this. If you do a resonance structure, then you can protonate that. Or protonate to form the most stable carbocation of an alkene, which is this, happens to be resonance stabilized, and then deprotonate. But that's all tautomerization is. If you realize this and practice with this, you're going to be ahead of a lot of students in Chem 345.